First of all, I would like to thank the organizers for giving me an opportunity to present this work here. So, as the title says, I'll be that's something. Okay, I'll be talking about some of the interesting discoveries we have made in Globular cluster 2005 with the MeerKAT telescope objects. And you should. Perfect. Yeah, so just to give a brief overview of what I'm going to be talking about, I'll first motivate why it's interesting to search for pulsars, specifically in Globular clusters, and what value is MeerKAT adding to this. Then I'll talk specifically about the discoveries we have made in 2005. And then finally, I'll just give some brief information about the kind of searches we are doing with Einstein at home. Okay, so we had a nice coffee break, but hopefully you've not forgotten too many things. But in case you have, I thought I'll just give a quick recap of the previous session. So the gist of MeerKAT is that it's the most sensitive radio telescope in the southern hemisphere, fully steerable dishes, large frequency coverage, capable of beamforming and producing hundreds of beams on the sky, and this makes it an excellent instrument for searching for pulsars. Specifically with that in mind, there is the TRAPPIM project, which is targeting certain kinds of sources to look for pulsars. And we already had talks from Colin, James, Michael, and Emma speaking about this. My focus will be specifically on certain kinds of sources which fall under the TRAPPIM bracket, which is globular clusters. Okay, so what are globular clusters from the perspective of pulsars? Well, first of all, it's a large collection of stars, about 10 power 5 order of magnitude. And it's mostly an old stellar population. So this in itself already says that it promotes neutron star formation. Apart from that, you also have very large core densities, much more than what you see in the galactic field. So that itself, that actually encourages different kinds of gravitational interactions. So that would lead to finding, forming different kinds of exotic binaries. And we already have some examples of that. So there is the fastest spinning pulsar currently known, the record holder, comes from a globular cluster. There's also the most eccentric radio binary pulsar, which is eccentricity of 0.96. So all in all, the gist is that if you want to find exotic binaries, globular clusters is a great environment to search. What is the status right now? We have very close to 300 discoveries in around roughly 40 clusters. And this is what has been plotted here. And of these, about 72 pulsars have been found with MeerKAT. So what I've plotted here is actually the period of these versus GM. As you can see, most of them are millisecond pulsars. Okay, the focus of my talk will be on this huge bar here, which has the most number of known pulsars we know currently, which is 1005. And also stay tuned for the next talk, which will be on NGC 1851. Okay, so I said I'll talk about 1005. So to give you some background about this cluster, it is the record holder for having the most number of confirmed known pulsars. It also has a large number of binary pulsars, in fact, and ranging from very eccentric systems to also spider type systems. It houses the fastest spinning pulsar, spinning at 716 hertz. And models predict that they're actually, their expectations to find many more. And one of the simple arguments is what I've plotted here from a paper in 2022, which is the log-in log-s argument. So what I've plotted here is pseudo-luminosity, which is luminosity, the intrinsic flux weighted by the distance to the cluster. And this is the number of known pulsars beyond a certain luminosity that I showed. Now, what you can see is if our searches are complete, this trend should keep going as a straight line. But what we see is actually it starts tapering, which says that our searches are actually incomplete and there are many more pulsars to be found. And keeping in complying with the theme of this workshop, I also thought I'll quickly motivate what are the different studies that have happened in different wavelengths. One is the fact that you actually, optical and near-infrared studies have shown that there are two different types of stellar populations and possibly two activities of starbursts, which actually complies with the fact that we find so many pulsars. And we also have a lot of association of known pulsars in X-rays. So, and apart from that, we also have detections in gamma rays. So this is an excellent cluster to search pulsars. Now we already have so many pulsars. So what is MeerKAT adding? This was like the details of the fact that we beamform and stuff like this was already mentioned in previous talks. So the gist is that previous searches had a lot of sensitivity gaps, which are actually going to be covered by the fact that you can place hundreds of beams within the same area in which it was searched. So the green circle here is actually the Green Bank telescope beam, which has been the most successful for finding pulsars in Terzan 5 previously. Now, the fact that you fill in these sensitivity gaps adds a great boost. And the fact that you can also localize pulsars better within these beams, and this also makes it convenient for following up in imaging. What I wanted to show with this plot is the fact that most of the pulsars are actually concentrated in close to the core of the Terzan 5 globular. Okay, so what was the search strategy? We wanted to go simple first. So we went for an FFT-based approach, just dealing with data in the Fourier spectrum. To account for the fact that we want to be sensitive for binary pulsars, we just used a linear acceleration approximation as a first try. And to be also sensitive to compact binaries, we actually segmented the data into as small as 30-minute chunks, which would make us a bit more sensitive to slightly more compact binaries. And Terzan 5 already has a wide range of DMs within it, and so we made sure that we have a wide range of DM in which we are searching. There are legacy software which actually does it, and this thing called Pulsar is actually a wrapper for Presto, and it's open source, so feel free to look at it. If whatever candidates we got, if we see it in 2 epochs, it's confirmed. And what we can leverage is the fact that there have been 20 years of data taken on Terzan 5, and so you could also always go back and put constraints on the parameters of the pulsars we have found with GPT data. So that is a real boost here. Okay, coming to what discovery. So one of the first discoveries we made was TERF5AO. This was the 40th pulsar which was confirmed. Thank you. 40th pulsar which was confirmed in the cluster. The spin period is around 2.27 millisecond, and it's in a wide orbit, 57 days, and it's actually eccentric. It has an eccentricity of 0.32. So based on this and based on evolution scenarios, you would think that how would such a highly recycled system be formed? So the idea is it's most likely an exchange product. This is not surprising given that it's a double cluster environment. So what would have happened is there's another companion which would have recycled the pulsar, and then it got flung out for a more massive pulsar. So the minimum companion mass we find is around 0.8 solar masses. We have also measured one post-Keplerian parameter, which is the rate of advance of periastron, and this can translate to an estimation of the total mass, which is roughly around 3.2 solar masses. And now we can, with this information and with the minimum companion mass, you can also constrain what is the maximum pulsar mass, and that turns out to be 2.2, which makes it very interesting. So if the system is actually edge-on, it could have a very massive pulsar. Not only that, if this is confirmed to be a double neutron star system, it would be record holder for 2 things. One is the fact that it's the longest orbital period for a DNS, and it was also the fastest spinning pulsar in a DNS. So what I want to do next is trying to understand if we can actually measure the individual masses, and maybe something like try to measure a Shapiro delay, for example, and trying to see if we can find radio pulsations from a companion, even though there's only one system known so far. Now coming to another discovery that I made. This is actually a spider type system. So there are 2 kinds of spider systems. One is black widows, and the other is redback. So the black widow has a lower companion mass. As you can see, it's around roughly 0.01 solar masses. Now, what's interesting, so you can also see in time here that there's an eclipse. It's actually, you don't see any emission here, which is typical of these kind of systems. What is interesting here is the fact that if I put all the known black widow systems, where I plot spin period versus minimum companion mass and spin period versus orbital period, this red dot here is actually this pulsar, and it's actually deviating from the population. So there might be something interesting going on in terms of evolution here. So this is what I want to explore further, and hopefully try to measure an intrinsic P dot to the system to actually give clues to this. Yeah. Now, another eclipsing system that I found was this thing. It's a redback. It has a higher companion mass. Now, one thing here we found was that even with 2 years of data, we needed a lot of orbital frequency derivatives to actually get a good timing solution. Now, this is because you find a lot of orbital period variability. The last slide from Colin's talk actually kind of justifies this. But that's not the most interesting part. The interesting part is from a study 3 years back, there was a point source that was pointed out, and they found X-ray pulsations with a periodicity of 12.3 hours. And they also found it in radio imaging with a steep spectrum source. And we have found the position and the orbital period from radio to be compatible with it. And we think we have actually found the radio counterpart to the system, which was predicted. These are just other discoveries we have made too. Binaries. There's another eclipsing black widow. I know I said in my talk that I'm talking about binaries, but I thought I'd quickly mention there was also an isolated pulsar we found. Okay, because I don't have too much time, I'll quickly go through some of the last slides I have. We want to search push the search boundary, basically push the search parameter space. We want to find, let's say, more compact binaries, which would be useful for doing tests of general relativity. The fact that we are constrained by a linear acceleration regime to only, let's say, orbital periods which are 10 times the t-orbs makes us believe, is there some way we can not compromise on segmenting the data and still being sensitive to these compact binaries? So what is the solution? We look for coherent algorithms which look at the full Keplerian orbital parameter space. This is not something new, it's been attempted before, but so far it's not found what it was intended for. So what can we do? Well, we have a great telescope, we have the right environment. We want to add more trials. So how do we get this? And send it home. So it's a volunteer distributed computing project. It's been running for many years now. It's actually not something new. It's been applied for data from Palfa, which is from Arcivo. Okay, from Arcivo, but now the idea is we have actually expanded it to MeerKAT data, and we are running it with 3 globular clusters currently. We are designing 2 different kinds of searches, looking for different kinds of companions with roughly these kind of maximum companion masses, ensuring that we can process the data in a reasonable amount of time. And we use only specifically GPUs, and when I say GPUs, about 10,000 GPUs. And we have actually been finding a lot of known pulsars blindly, and there are a lot of interesting candidates which we are hoping to follow up. And I will leave you with my summary and conclusion slide.
Okay, go ahead.
Yeah, this is more of an open-ended question. What do you think controls the number of pulsars or binary pulsars in a globular cluster?
That's a lot of things. So it's a multi-variable problem, I would say. So one is the fact that, so I'll give you an example. So there are something called core collapse globular clusters where you tend to find more mass in the center. But what happens there is you also have more exchange interactions, so things get flung out. So what happens there is you actually find more isolated pulsars than expected. So it needs to be a fine balance of something that does not get flung out too much, but also ensuring that the binaries can be compatible with each other. So you need to be a balance between those two things.
So at the very beginning, you showed that the vast majority of pulsars in globular clusters are millisecond ones, but what about the ones that are not millisecond ones? How did they get there?
That's a good question. So one is, again, the fact that I said many things are flung out. So one could be young pulsar which got flung out. Apart from that, if you're talking about actual pulsars with young pulsars there, you wouldn't expect that given that it's already a multistellar population. So it's most likely the first argument, which is the fact that it's a young pulsar from a binary which got flung out from the system.
But so I can make a comment on that. So
yeah.
You can see these apparently young pulsars. By young, we mean 100 million years.
Yeah.
You see them in core collapse volume. So one thing you can get that kind of thing is if you start recycling the Neutron star, and then you drop the little matrix very binary because of the very high stellar interaction rate, there's actually a chance of disrupting the accretion even when you have an LNXV that is recycling that previously had recycling. So that explains why these apparently in pulsars appear predominantly in the core collapse photos.
But they still have, the neutron star itself is still billions of years old, right?
It's still many millions of years old, and actually, if you look at the PP dot diagram, they all consistent with the recycling curve, so the spin period, B field equilibrium line. So it's consistent with them having been recycled, although only partially.
Thank you.